Oh, hey, you might be wondering why I'm divided into pieces, right? Well, that's because today's topic is the division theorem. Alright, that was a terrible one, sorry for that. But anyway, today we're gonna state and prove this interesting concept. I hope you enjoy it. Known as the division theorem, division algorithm, or even, according to Wikipedia, Euclide's division lemma, this statement is a very important concept in number theory. It says that given two integers a and b, with b greater than 0, there exist unique integers q, quotient, and r, remainder, such that a is equal to b times q plus r, and 0 is less or equal to r, which is less than b. In simple words, it says that an integer a can be divided by a positive integer b in such a way that the remainder is less than b. For example, say we have two integers, 4 and 3. 4 can be written as 3 times 1, the quotient, plus 1, the remainder. Look, although this theorem is often called division algorithm, notice it's not an algorithm at all. However, it paves the way to a simple method for dividing whole numbers, the repeated subtraction method. The method itself is an intuitive notion on division for positive integers. If we divide a by b, we try to subtract b from a as many times as possible while trying to keep the result non-negative. After doing that, we are left with the remainder, which is 0 if a is a multiple of b, or some other non-negative integer otherwise. Yeah, it's that old thing many of us learned to do with cookies and friend sharing contexts. The proof is normally divided in two steps. First, we prove the existence, that we can write the integer that way. Then, we prove the uniqueness of the expression, that there is only one way to write with that form. Here, it's useful to remember our division by repeated subtraction. The remainder of a divided by b is found subtracting b from a as many times as we can while we keep the result non-negative. That is, r equals a minus q times b, where q is our quotient and r is our remainder. Q times b is some multiple of b. Anyway, let's say a equals 21 and b equals 6. Then, we're going to consider the set of integers that result from subtracting from 21 some multiple of 6. This set contains the elements 3, 9, and 15. We see 3 is the least element and now our remainder. Well, sure, as expected. You can try it with the cookies. No matter what, you will be left with 3 cookies and will have to fight over it. Okay, just kidding. But for a more general case, as above, r equals a minus q times b, we need to show that the equivalent set of these subtractions is non-empty, and, furthermore, that this least element exists. For this matter, we will use the well-ordering axiom, but we will discuss this later. To prove existence, we first consider the following set S whose elements are a minus xb, where x is an integer and a minus xb is greater or equal to 0. Yeah, this is pretty much the set we were talking about just now. We then must show that S is non-empty. Nice. To do so, following the definition of S, it suffices to exhibit a value of x that makes a minus xb non-negative. Well, sure, if a is greater or equal to 0, then x equals to 0 is a cool choice that gives us a minus 0 times b, which is a itself. However, if a is less than 0, since b is a positive integer, we have multiplying both sides by minus a, and that's equivalent to, that yields x equals to a as a solution that makes a minus xb non-negative. Conclusion, the set S is non-empty. We are now going to use the well-ordering axiom, which in case you don't know, says that any non-empty set of non-negative integers has the smallest or least element. Since S only contains non-negative integers, we know it has a smallest element. Let's call it R. By definition, R is of the form a minus xb for some x, say x equals q. You see, we've just shown that there are such integers q and r for which a is equal to q times b plus r. Alright, but you might be wondering about the choice of r as the least element. There is a reason. Remember from our initial statement that R needs to be greater or equal to 0 and less than B. We still need to show that this is the case for our choice of R. We know R is greater or equal to 0 because it's an element of S. But to show it's less than B, we suppose on the contrary that R is greater or equal to B. Then we have R minus B is greater or equal to 0. But since R minus B is the same as A minus Q times B minus B, we can simplify and we get A minus B times Q plus 1. And this has the proper form to be an element of S. However, since B is positive, we know R minus B is less than R, or A minus B times Q plus 1 is less than R. That's a contradiction. Why? Because we chose R to be the least element. But here, A minus B times Q plus 1 is also an element of S said to be less than R. Anyway, we then have that R is less than B. Awesome! We've just found integers Q and R such that A is equal to B times Q plus R and 0 is less or equal to R less than B. For the next step, we still have to prove the uniqueness of Q and R. We begin by supposing that A has two of the desired representations, say B times Q1 plus R1 equals to B times Q2 plus R2, with, of course, 0 less or equal to R1 and the same for R2. Our goal is to show that necessarily Q1 is equal to Q2 and R1 is equal to R2. So let's assume that R2 is greater or equal to R1. Then our former equation implies since B is greater than 0 and we are assuming that R2 is greater or equal to R1, we know that Q1 minus Q2 is a non-negative integer. Therefore, R2 minus R1 is a multiple of B, which is clear if you move R2 minus R1 to the other side of the equation. But look, since R2 is greater or equal to R1, and they are both greater than or equal to 0 and less than B, we know that from the fact that the only multiple of B that is between 0 and B itself is 0, that R1 minus R2 is equal to 0, and hence R1 is equal to R2. Substituting the value for R2 minus R1 here allows us to conclude that Q1 is equal to Q2. Similar reasoning for R1 greater or equal to R2 leads us to conclude uniqueness once again, which completes our proof. Hey guys, thanks for watching till here. Hope to have helped, and see you next time.